Hi, I'm Ramin Mojab, and in this video I'm going to talk about the concept of random variable. This is the third session of my program on statistics and econometrics. You must be familiar with the probability space. In the previous sessions I tried to explain it. In this session we'll talk about an interpretation of this part, the first element, which is the sample space. And for this interpretation, we need a tool which is known as the random variable. And of course, in order to provide a proper definition, we need some other concepts such as Borel sigma algebra on R, or preimage, or measurable function. A random variable is actually an example of a measurable function. I will also discuss two other concepts: distribution function and cumulative distribution function. As an introduction, let me talk about this system of equations. X is a real number, and at the same time x is 1, and at the same time x is 3. You know that this system of equations, or this system of linear equations, is inconsistent and it has no solutions. Okay, however, let's try another way, and let's define two other variables. X minus 1 equals epsilon 1 and x minus 3 equals epsilon 2. And these are errors. For example, if epsilon 1 is 0, then this equation is satisfied. The same is true for epsilon 2. If epsilon 2 is 0, then this equation is satisfied. And we define a distance and we try to minimize that distance. The distance is sum of squares of errors. In other words, we find an x in R and we minimize epsilon 1 squared plus epsilon 2 squared. The solution to this optimization problem, you can guess the solution, is x star equals 2. Of course, I will talk about this optimization problem later. It is known as ordinary least square estimator. However, this solution is the solution to this optimization problem and is not a solution for this system of equation. And we need something else. We need something more. In fact, we should generalize this condition, x in R, and we should introduce some other concept. In order to generalize x, we can use the concept of random experiment that we have talked about it in the previous sessions. Here, x can be related to an elementary outcome. For example, assume that an athlete is practicing shooting at an archery target, and x is his score. In other words, his first score is 1, his second score is 2, and now we want his second score is 3, and now we want to predict his third score. Now this optimization problem makes sense, and it's a good choice to say that his next score is going to be 2. However, here x is not just a real number. X is related to an elementary outcome, and x is related to a random variable. We are going to talk about this x, which is a function of the elementary outcomes. In this example, let's assume that you have accepted that if the next score is less than 3, then you will win $10, or you will get $10. Otherwise, you should pay $5. And your profit is a function of the elementary outcomes, or the obtained elementary outcome. If 0 is obtained, then you will win $10, or your profit is 10. If, for example, 4 is obtained, then your profit is minus 5. Therefore, your profit is a function of the elementary function of W, the elementary outcome, in which W is in omega, or your profit is a function from omega to R. This is the random variable that we are going to talk about. However, we need to address an important question. Do we have enough information regarding the codomain of this function? Or, in other words, for example, can we calculate this probability that profit is in this interval? Or can we calculate the probability that profit is not negative? In order to be able to calculate this probability, x or this function should be measurable. I'm going to talk about this concept in the next slides before I define the random variable. We want to interpret the sample space by a function or something. We can say that we want to transform this probability space to a new one. Since our interpretation is a numerical one, then we use the set of real numbers here as the sample space of this new probability space. However, we should talk about the second element, which is the sigma algebra. One candidate is the Lebesgue sigma algebra, that Lebesgue measure is defined for all its members. Okay. Of course, we do not use this candidate. Instead, we use a subset of Lebesgue sigma algebra, which is known as the Borel sigma algebra on R. We talked about it before. Borel sigma algebra on R is generated by any of these collections, the set of all open intervals in which the bounds are rational numbers, or the set of all closed intervals, and so on. For example, the set of all open intervals from a rational number to positive infinity. As I said before, the union of these intervals or set of numbers are all in this Borel sigma algebra. For example, Q is in this sigma algebra. Okay, why do we say that the bounds must be a rational number? Recall that Q is a countable set, and we want a collection of sets, and therefore we use Q here. And just by the definition of the generated sigma algebra, we need a countable set here. And you must be familiar with the concept. Therefore, you can answer this question that, for example, why the complement of Q, or the set of irrational numbers, is also in the Borel sigma algebra. We need this concept to be able to define the random variable. Let f be a function. The preimage of a subset of the codomain under f is a subset of the domain. Here x such that fx is in A. This is the preimage of A under f. Okay, let's have some examples. For example, x cubed, and the preimage of this set x such that x is in this interval under f. It is x such that x is in 1 and 3. You can see this on in a graph. For example, this is x cubed, and if this is 1 and this is 3, then we have 1 and 9 here. Therefore, the preimage of this subset of the codomain under f is 1 to 3 here. Consider another example, x squared. Here the preimage of this subset of codomain under f is 2 and 3. Is that all? The answer is no, because -2 and -3 is also in this preimage. For example, if this is x2 x squared, then and this is 4 and this is 9, then you can say that, for example, here this is -2, this is -3, 2, and 3. The preimage of this set, 4 and 9, is this set. And another example, a function of two variables, x1 squared plus x2x squared. Here the preimage of this subset of the codomain x such that x is in this interval. I'm not going to write the codomain. It's a ring. I want to show this one. For example, if this is x1 and this is x2, then the preimage is this ring. Okay, for example, this point is x2 is 2 and x1 is 0. 0 plus 2 squared is 4, and it's a member of this one. Or this point, x2 is 3. 0 plus 3 squared is 9, and it's in this subset. We should talk about this concept too, a measurable function. Recall that we want to transform, for example, this probability space to a new one in which the first one is R, second one is Borel sigma algebra, and we have not yet talked about this part. Anyway, this function, the measurable function, generally does this transformation. Okay, let omega 1 sigma 1 and omega 2 sigma 2 be two measurable spaces, and this function from omega 1 to omega 2 is called sigma 1 sigma 2 measurable, or simply sigma 1 measurable function if the inverse image of A for all A in sigma 2 the inverse image of A under F is in sigma 1. Or you can say for all members of the codomain we can find information in the domain, or for all members of the information set of the second probability space, we should be able to find information in the information set of the first probability space. Note that sigma algebra is our information set. Now we can define the concept of a random variable. Let this order triple to be a probability space if this function x from omega to r is a sigma measurable function, then x is a real random variable. And x of w, in which w is an elementary outcome, is a realization of x. And we can also define the distribution function p sub x of a is p of the inverse image of a under x, in which a is an interval. It's a member of the Borel sigma algebra. This is known as the distribution function of x. You might use this notation. For example, x is, you're familiar with this notation, x is normally distributed. And we might use, for example, this one, simply this one, p of x in A instead of this one. P, the inverse image of A under x is, or this one, p sub x of A. Or we might simply use p of x equals b, or p sub x of b instead of, for example, this set, p sub x of this set, or the inverse image of this set under x. And similarly, this one, p x is less than or equal b instead of this inverse image, or this set. Let's talk about the measurability condition. We have this order triple. This is the probability space, and each member of sigma is a measurable set, and we can calculate its probability. Now, p of P sub x of A, the distribution of x in A for all A in B, is it defined or not? This is an important question. We know that this probability equals the probability of the inverse image of A under X. And this, since X is a sigma measurable function, this part is in sigma. Therefore, we can calculate its probability. Therefore, the answer to this question is yes. Okay. Also note that the inverse image of A under X is this set, W in omega, such that X of W is in A. Of course, we'll talk about this in some examples later. As an example, consider a probability space in which the sigma algebra is a trivial sigma algebra. It has the minimum available information. Now consider an experiment in which a coin is tossed and the sample space is H and T, and regardless of the outcome, you win $10. Okay, whether H is obtained or T is obtained, you win $10. Here, for any A in the Borel sigma algebra, the inverse image of A in under X, we said that X in omega, W in omega, such that X of W is in A. And here, this is whether the empty set or omega, which means that its probability is whether 0 or it's whether 1. Okay, for example, here the probability that X is less than, for example, 10, this is 1, or the probability that X equals 20 is 0, and so on. Here we cannot define any other random variable, for example, like before, that if H is obtained, then you win, for example, $5, or if T is obtained, you lose $5, and you cannot define these random variables when you have this level of information, because in this case, these random variables are not sigma measurable. As another example, consider another experiment in which a dice is tossed. If W in this set is obtained, then you win $W. Okay, and this is an interval, and it's a member of the Borel sigma algebra, and you know that its inverse image under X is W in omega. This is omega, this set is omega, such that X of W is less than 0. I'm using this inequality here, and you should know that this is an empty set because we defined our random variable here, and W is never a negative number. Therefore, this is the empty set, and therefore the probability of the inverse preimage of A under X is 0. Or you might write the probability that X is less than 0 is 0. Or again, you might write P sub X of A is 0. Of course, you cannot, for example, write Px of P sub X, X less than 0 is 0. We did not define this one, but we did define this one. Another interval, X is equal or less than 1. The preimage of B, here we have B, under X is, we can write this set, X a set of one element 1, therefore its probability, or the probability of this x inverse of b is 1/6. The same, you can write other functions here too. Let's consider another interval. Here the inverse image of the preimage of c under x is 1 and 2, and therefore the probability is 1/3. Here the inverse image of d under x is omega, because x is always greater than 1, and therefore its probability is 1. In this example, I use the experiment of the previous example. A dice is tossed and W is obtained. However, X is defined in another way. If W is 1, 2, 3, or 4, then you win $1. If W is 4, 5, or 6, then you win $2. We do not talk about the measurability of this function because x is not a function. Recall the definition of the function here. If W is 4, then x of W is can be 1, and x of W also can be 2 here, because we have 4 here and 4 here. Therefore, it's not a function, and therefore it's not a random variable. There is an exercise here. Let x be a real random variable with values in this probability space. This means that x is sigma measurable. Okay, we want you to show that p of x, or p sub x, or the distribution function, is actually a probability function. The preimage of the empty set under x is the empty set. I explained some parts, and therefore you can easily show that px at the empty set is 0. This is the first axiom of probability. Here the preimage of r under x is omega, therefore the px of r is 1. Note that we are actually dealing with this probability space in which the sample space is R. Here we have the Borel sigma algebra, and here we have P of X. Okay, and this is the value of the measure of the function, the measure of the sample space. Okay, and since P is not negative, then Px is not negative too. Here, for the last axiom, you should show that this equality is satisfied. This part is P of this preimage, the preimage of this union under X, and this preimage is this set, W in omega, such that X of W is in this union. Try to explain why this is equal to the union of the preimages, which means x inverse, the preimage of ai under x, and you should use the definition of a function and show that these are separate events, and therefore you can use the last axiom of probability for p, and therefore the last axiom of probability is satisfied is also true for p sub x, or the distribution function. There are many types of intervals in the Borel sigma algebra, or in other words, there are many types of measurable sets in Borel sigma algebra on R. It might be an open interval, a closed one, a number, or a set of numbers. We need an agreement here, and this is why the cumulative distribution function is defined. and agreement is on this interval or this set. The value of the distribution function at this set is the cumulative distribution function for a given b. Okay, and note that no information is lost. For example, we can use, if we have the probability that x is less than b, less than or equal to b, and we want to calculate the probability that x is greater than b, then we know that this is the complement of this part. This interval is the complement of this interval, and we know that p of e equals 1 minus p of it's the complement of e here, and therefore we can easily calculate these probabilities. Or if we want to calculate the probability of x is that the probability that x is between two numbers, or the probability that x equals a number, we use this limit, or the probability that x, for example, is equal or greater than b and less than positive infinity, we use this union. And therefore, in other words, there is no loss of information here in this agreement. We can prove some propositions here. Let x be a real random variable. The CDF at positive infinity is the probability that x is less than or less than positive infinity, which means the probability of the preimage of r under x, which means the probability of omega, and this is 1. Here we have the probability, the CDF at minus infinity, which is 0. We have the probability that x is less than minus infinity, which means the inverse, the preimage of x, this set x less than minus infinity, and this is the probability of the empty set, and this is 0. And here we say that the CDF is a non-decreasing function. Why? Because the CDF at a is equal or less than the CDF at a plus a positive number. Okay, and which means that the CDF is a non-decreasing function. Here we have a, this x such that x is less than or equal than a, and we have b for this part, x such that x is less than or equal a plus a positive number, and we know that a is a subset of b, and therefore the probability of a is equal or less than the probability of b. Note that by these properties, the distribution function, the cumulative distribution function, if this is f of b and this is b, is between 0 and 1 and is a decreasing number. It starts from 0 and it is increases, or it does not decrease until it reaches positive infinity, until it reaches 1 at positive infinity. Thanks for your time. In the next session, I will talk about the expected value of a random variable. Please note that I'm still learning statistics and any comment is appreciated.